Well, hello everybody. We've given you quite a taste over the last couple of days of an introduction to integrals, and specifically we've put all of our energy into evaluating definite integrals, integrals that had bounds on them, integrals that measured the area bounded by a curve in the x-axis and two vertical lines, and our final answer to those was just a finite numerical answer. Today, before we can go any further with definite integrals, we've got to call time out and take a step back, and we're going to look at some basic integration rules and really get ready to, instead of evaluating these geometrically or evaluating them by approximating with Riemann sums, we're going to talk about how to do it algebraically and really focus on our analytical methods here. So our first one here, just a couple definitions. Integration is the process of finding the antiderivative. And I think the name suggests that we're just going to reverse the process that we've been doing. The antiderivative is also known as the indefinite integral. And let's see here. You can probably hear Bailey snooping around here a little bit. Wants to see what's going on. Now, integration is the reverse. Probably a more mathematical word for that would be the word inverse. They're just inverse operations. You know, what one does, the other undoes. And the symbol by now you've seen is this big, tall, skinny S-looking symbol. Well, there is one really interesting phenomenon, and maybe you've seen it in the last couple of videos. When I would do an example of an indefinite integral, I would always throw a plus c on the end of my answer. And the reason it has to do with this idea of being a general solution. In other words, think about this. What if I gave you y equals x squared plus 6? What if I gave you y equals x squared minus 4? Or what if I gave you y equals x squared plus 100? What do all three of those functions have in common? What they all have in common is the exact same derivative. The derivative for all of those functions would be 2x. So in other words, when we try to reverse the process, when we try to integrate 2x, we don't really know what the constant should be. So we're safe in saying that the antiderivative of 2x is a term called x squared. But how do I know whether there should be a plus 6 or a minus 4 or a plus 100 dangling at the end? And so what we do is we say, well, we don't know for sure, so we just say we acknowledge the fact that there is a constant, and we just simply don't have enough information to know what the constant is. So we always throw a plus c at the end of every single antiderivative we do. And just to acknowledge the fact that there could be a constant there. Now, how are all those functions related to each other? Well, here's a nice picture. We call this a family of general solutions. And I think it kind of makes sense because the idea of family comes from the fact that all of them are related somehow. In fact, all of these functions on this picture, there's 5 of them total, they all have the same derivative. And what you'll notice, though, is they're kind of mirror images of each other. The only difference is they're just vertical translations of each other. You know, so you could slide these functions straight up or straight down, and they'll still have the same slope at the same moment as long as you don't stretch them. We're just sliding them up and down. Okay, the first rule we're going to throw at you is called the constant rule of integration. Very simple, basic rule. And all it says is that if you want to integrate a constant with respect to x, the antiderivative is going to be the function kx, and then again plus c. All right, just think about that. Sometimes we try to think of the reverse process. If you were deriving, if we tried to take the derivative of 2x, the derivative would be a constant 2. So all we're trying to do is we're trying to go this way instead of that way today. So a couple of examples here. If I wanted to integrate the function 4, I would say the antiderivative is 4x plus c. If I wanted to integrate pi, just remind yourself pi is a constant with respect to x, the answer would be pi x plus c. Or if I wanted to integrate 6 with respect to y, always watch the notation that closes out the integral. The antiderivative in that case would be 6y plus c. Our second rule is called the power rule for integration. And I think this one's going to make a lot of sense once you think about it. Things are going to get a little hairier because we're going to have fractions and stuff like that, and that always seems to complicate the process. But what if we just wanted to integrate a basic polynomial term? All right, and that's whenever I say power rule, that's what I want you to think of. I want you to think of a basic, well-behaved polynomial term. All right, and in this case, what we're going to do is we are going to add 1 to the exponent, and we're going to divide by the new exponent. and throw a plus c on the end. And you know, think about how we used to differentiate. It's just the opposite. You know, we used to subtract one from the exponent. We used to multiply by a new coefficient, not divide. So everything's the inverse or the opposite. Now sometimes we like to rewrite it as, you know, 1 over n plus 1 being the coefficient times x to the n plus 1 power. That's just another way of writing and expressing the same thing that we have above. So we're going to have to talk ourselves through it. You know, we'll definitely do several examples. But I was just thinking, you know, what if we had to integrate x cubed? Probably something that you could do in your head. But what I'm going to do is I'm going to say I need to add 1 to the exponent, and I'm going to divide by the new exponent. And of course, you could rewrite that as 1/4 x squared if you preferred that notation compared to the original one that I wrote right here. Now here in this slide, I've got 2 special properties of integrals for you, and I don't have any fancy names for them or anything, but they're just little itty-bitty tricks that are going to really just simplify the process for you. And number 1 goes like this. If you have a multiple of, you know, a function, k times f of x, okay, so k is a constant, and then f of x is, of course, a function, you are allowed to move the k outside and basically put it on the shelf for the time being, and just focus on integrating f of x rather than integrating the multiple of f of x. So that's a nice little trick you'll see me use a lot of. The other one says if you're integrating the sum of 2 functions, maybe we've got g of x plus or minus some other function, basically you know, a binomial or a trinomial or something like that, you're allowed to rewrite that as the sum or difference of 2 individual integrals. So you could really focus on just integrating g first, and then you can put all your energy into just integrating f of x rather than trying to be overwhelmed by integrating both of them at the same time. So here's a very basic 4-step process that I think is really simple, but it's just going to help you organize your thoughts as you go through, and we're really going to focus on this in class tomorrow in the first set that we do, just again to get our basics down and get our feet underneath us. But what if I gave you the function y equals 1 over the cubed root of x squared, and I wanted to find the antiderivative of that function? One of the things you're going to find out is it's always best to try to rewrite the function so that it's not in terms of a fraction. So what I'm going to do is I'm going to rewrite it as x raised to the negative 2/3 power. So notice up to that point right there, I haven't done any calculus at all. I'm just using some basic algebraic skills to rewrite that function. Next, we want to actually integrate it. Here's where I'll use my power rule. I'll say, the integral or the antiderivative is x to the 1/3, because I had to add 1 to the exponent, and I'm going to divide by the new exponent, okay, and then I'll throw my plus c at the end. And now just rewrite that so it's just in a cleaner, more simplistic form, and dividing by 1/3 is the same as multiplying by 3, x to the 1/3 plus c, or you could even say 3 times the cubed root of x plus c, whichever form is, preferred. Well, just like as with anything we do in math, we're going to need a ton of practice and a ton of reps. I think conceptually it's a very basic concept that you're going to build confidence with quite quickly. But there is no substitute for getting the reps in that we need, and there are no shortcuts here. So certainly tomorrow's assignment in class is we're probably going to do about 200 examples in class just to really build that muscle memory. But here's the general directions that I want us to assume. When they ask us to evaluate an indefinite integral, I want you to assume that they don't want us to leave any negative or fractional exponents in our answer unless otherwise stated. Now, the first thing that caught my attention here is, like, right now I have the product of 2 functions, and I certainly haven't, seen any special product rule for integration yet. So we're going to avoid that. All I'm going to do is I'm going to distribute the x through. Again, we're not using any fancy calculus yet. We're just distributing an x. 3x squared plus 4x dx. Now I'm going to take advantage of one of those special properties that said, you know what, I don't have to evaluate all 4 of these at once. I could really just, trim this down and focus on evaluating, 4 separate smaller problems individually. And I'm just going to watch my signs. We've got 3x squared dx, and I'm going to finish with the integral of 4 dx. And I'm going to use my power rule on the first 3 terms, and I'll use my constant rule on the very last term. And so the antiderivative, let's see, I'm going to add 1 to the exponent and divide by the new exponent. Again, we're going to add 1 to the exponent, divide by the new exponent. Let's see. add 1 to the exponent, divide by the new exponent, and then my constant rule is just it was kx, but now it's going to be 4x, and then at the end of all those terms we'll throw our plus c, and then if you had to rewrite it anyway, just to overstate the obvious here, we could say 2/5 x to the 5th minus 7/4 x to the 4th plus x cubed plus 4x plus c, and I bet you feel pretty comfortable about that last step. So we've reached deep into our bag of tricks, and we've pulled out a real ugly, feisty-looking problem here. And the first thing I want you to do is just recall the 4-step process that we introduced you to moments ago. The first thing, if this is the original function here, step 2, I just want you to rewrite it so that we can get it out of radical form and see the fractional exponent. So I got x to the 1/2 plus x to the 2/3. Minus 1/3 is my coefficient, and x to the negative 1/2 is my exponent right now, and then 2 times x to the negative 3 power. Now again, just like the last problem, I'm going to really focus on just integrating these one term at a time. So again, I'm just rewriting. I've got x to the 1/2, and certainly if you're feeling pretty confident here, great time to hit the pause button and run through the antiderivative all on your own. Let's see, we got 1/3 x to the negative 1/2 dx plus the integral of 2x to the negative 3 dx. And I'm going to focus on integrating each term. So the first term, I'm going to add 1 to the exponent, so now it's 3/2, and I'm going to divide by 3/2. Let's see, I'm going to add 1 to the exponent. Now, like on the last problem, when I said add 1, I'm really thinking I'm going to add 2/2, and on this one I'm going to add 3/3, which gives me 5/3 for my exponent, divided by 5/3 as a coefficient, minus, let's see, I've got my 1/3 already in place. If I add 1 to the exponent, the new exponent's 1/2, and I'm going to divide by 1/2. And last but not least, if I add 1 to a negative 3, I get negative 2 divided by the negative 2, and I got a plus c there dangling at the end. So just now, now the calculus part's over. We're just going to clean this up a little bit. Dividing by 3/2 is the same as multiplying by 2/3. X to the 3/2 plus 3/5 x to the 5/3. If I divide these coefficients, let's see, 1/3 divided by 1/2 is equivalent to saying 1/3 times 2. So I've got 2/3 x to the 1/2. And then at the very end, I've got minus 1 over x squared plus c. And ladies and gentlemen, there's my final answer. There's my antiderivative to a very feisty problem that we started with. You'll have a good chance to laugh at yourself at times when you're working on these problems, because some of our biggest challenges are, when we say add 1, you're like, how tough can adding 1 be? But by the time we mess with all these fractions and stuff, it can be rather goofy. And then just the cleaning up process of dividing coefficients and working with cleaning up those fractions and so forth. But all in all, it's not going to be a bad day. So my last 2 problems there show 2 of the most popular tricks. Again, there's no such thing as quotient rule for integration. So what I want you to do now is I want you to use a trick called make like a beaver and split this one up. In other words, we're allowed to say this: the fraction x plus y divided by a is really x divided by a plus y divided by a. And technically in math terms we call that decomposition. I just call it make like a beaver because beavers like to split wood, and we're splitting this one big fraction into 2 smaller, more manageable fractions. So if you ever hear me say that goofy saying, you kind of get an idea of what I'm trying to imply. But what we're going to do here is we're going to say 3x to the 4th divided by x cubed plus 2x cubed divided by x cubed minus x divided by x cubed plus 4 divided by x cubed. And we're going to put all of our energy into cleaning this up. We're really not in a big hurry to integrate. I just want to clean it up, and I say this first term's 3x, and then I got a plus 2 minus, let's see, what would that be? 1x to the negative 2, and then the last term would be 4x to the negative 3. So not only did I, subtract coefficients, or exponents, I should say, but I rewrote each term so that there was no more fractions involved. I'd rather see negative exponents at this point than fractions. All right, now we're ready to integrate. And let's see, I've got 3x squared divided by 2, plus there's my constant rule, 2x, minus 1x to the negative 1 divided by negative 1. And last but not least, we've got 4x to the negative 2 divided by the new exponent, and then we'll throw our constant of integration on the end. And down the home stretch we come. Let's see, we got 3 halves, x squared plus 2x. Looks like plus 1 over x and minus 2 over x squared plus c. You know, if we have any questions about how to clean up some of these terms with their negative exponents and stuff, just give me a holler tomorrow and we'll work on reviewing some of those basic skills. But I think right here I've got my best version of my cleaned up answer, my antiderivative. Now there was one more problem here hiding at the end. And I can't stress this enough. When you're squaring that binomial, right off the bat, let's go ahead and get this rascal all FOILed out. Alright? And I don't have much room there, so I'm going to slide down here and start a new fresh page. Let's see. So I'm just going to take my time and I'm going to say, let's go 2 radical t minus 3t times itself, 2 radical t minus 3t. And certainly if these t's, you know, make you panic, you can certainly rewrite them as x's as long as you're consistent all the way through. So as I'm foiling, I'm going to get 4t minus outer times outer is going to be 6t to the 3 halves. All I did is I added my respective exponents. 6t to the 3 halves, and then plus 9t squared with respect to t. Let's go ahead, we'll integrate each term individually. And let's see, the first term is going to be 4t squared divided by 2 minus 6t to the 5 halves if we add 1 divided by 5 halves. Oh goodness, why am I doing that? I should have combined these two terms. You should yell at me here. That's minus 12t to the 3 halves. So as I integrate that rascal, it's going to be minus 12 as my coefficient right here. Getting a little messy, but of course the exponent and then what I'm dividing by would be the same. And then my very last term down at the end would be 9t cubed divided by 3. And just a little bit of cleanup, let's go 2t squared. Now here's a catch here. If I want to do 12 and I want to divide by 5 halves, I'm really multiplying by 2/5, and that's going to give me 24/5. So minus 24/5 t to the 5 halves. Oops, that 5's there. Okay, plus 3t cubed plus c, and boom, there is my antiderivative or my indefinite integrals answer. It's certainly a function. It's a function. It's created a family of functions. We do call this a general solution, just to recall from earlier. And ladies and gentlemen, I think you're ready to rock and roll tomorrow. So good luck, and we'll see you.